and as well as the lab sessions that we are going to cover. For fluid mechanics, thermodynamics is easier, but fluid mechanics has more applications than the thermodynamics 1. Thermodynamics 2 has more applications than the fluid mechanics, but for the easiness of the subject, fluid mechanics is harder than the thermodynamics 1. So what are the topics? The topics for the semester are, we will have the basic concepts firstly for today's lecture, and if you can't finish, for the tomorrow's lecture. And the basic concepts, these are the subtitles, for example, the application areas, states and properties, specific volume. The microphone of someone's microphone is open. No. Okay. These are the subjects for the thermodynamics 1. Firstly, we will cover the basic concepts, and then we will talk about the energy and the energy transfer, and then the properties of pure substances. Okay, so the topics for the other ones, so subtitles, we can say, it will be visible in the future. For example, when you are in energy and the energy transfer lecture, you will also see the subtitles for the lecture. And then we'll talk about the properties of pure substances. Okay, so especially water and the air. So we'll look at their properties. And then we will analyze the closed systems for the next one. And then open systems, we will analyze it, energy, and then second law of the thermodynamics. With this one, we will finish our semester. Okay, this is the roadmap. We can say the roadmap for the semester. And then the lab sessions, we will have the pressure measuring device for the first lab session, and then temperature measuring devices for the next lab session, and the boundary work, and then these are the lab sessions. Okay, so boundary work, and then we will have the energy calculations of components of heat pumps. This will be the next, and the refrigeration unit. We have a refrigeration unit, and this will be the lab session for the next one. And for the lab rooms, the rooms are the same as the name of the subject. For example, the fluid mechanics lab room, you have it, and the devices are for fluid mechanics. Okay, so good. So we have some quotes here. So first quote is from Einstein, and it says that the classical thermodynamics is the only physical theory of universal content which I'm convinced will never be overthrown. If this is the Einstein quotation, so there are some quotations that I've collected for you that can be interesting. And this one is the Maxwell's quotation, and says that second law is true as the statement that if you take a glass of water and put that glass of water into the sea, and you cannot get the same water back. Okay, if you put that glass of water into the sea, you will have the mixture, and then that mixture will not give you the same water, the same features, properties of the water back to you. And this is the same as the second law of the thermodynamics. And then comes the Klein and Nellis statement. It says that no other engineering science achieves such a broad range of applicability based on such a simple set of postulates. And when we see the postulates, means the laws or the rules. Okay, when you see the topics in the future, and you will see that there are only 3 laws in thermodynamics. The one is the first zeroth law and the second law. Okay, these are very important laws, but all of the problems are only solved by 1 or 2 laws. Okay, there are 1 or 2 formula to solve the problem, but it is very simple subject. The subject is very simple, but the difficult one is to understand the problem, because there are 2 formula, but infinite number of problems. You have to understand the problem, apply those 2 formula to the problem. Sometimes you have to get good approximations Therefore, understanding problem in thermodynamics is the first important step. Okay, if you understand the problem, the rest you can solve it. But if you don't understand the problem, you cannot do anything. So I will iterate it once more. You have two formula in thermodynamics. Okay, two formula, but lots of equations, lots of problems. Okay. Therefore, you should understand the problem. Sometimes you have to do a lot of approximations, and you say that this term is much larger than the other term, therefore I can neglect it, or I cannot neglect it. Therefore, understanding the problem is the major important step. If you understand it, the rest is okay. It says that, therefore, simple set of laws. And the applications of thermodynamics, so I have collected some applications for you. Let me show it. So the applications I've collected for you is that a life with and without thermodynamics. Okay, so when we think that there is thermodynamics and when we think that there is no thermodynamics. Okay, so I will show some examples to you. And the first example is that something is missing. Okay, in this example is heating system. You don't have any heating system, and therefore everywhere is ice. And this is one application of the thermodynamics, that you should have the heating system. At your home, you have everybody at his home has a heating system, and therefore this is very important application of the thermodynamics. And this is the heating system that we are using at our homes. And sometimes you are using for your clothes, and sometimes you are using for the heating of the room. Okay, anyway, this is the first important application of the thermodynamics. Second important application of the thermodynamics is that you can see the crash of the airplane. So it means that something is not right, and that something is, what is that something you think? You will have the engine. Okay, so this aircraft engine and this aircraft engine is not right. Therefore, you have this beautiful picture. Another application is the engine. So you can see the engine. So here you have the engines of the aircraft. Okay. Next one is here you can see it is very hot, and the dog wants to cool off, but something is missing, and that something is the air conditioner. Okay. Again, it is the application of the thermodynamics. So you have the air conditioner and you are happy. And in summertime, you always need it. Okay, so you see the applications, and some of these applications are for thermodynamics 2. Okay, for thermodynamics 1, we are only dealing with simple systems. Sometimes you will have the applications till the end of the semester. At the end of the semester, you will have the applications. But here in thermodynamics 1, we are mostly talking about simple stuff and the components of the cycles. Okay. Then here we have missing problem. So we have something is not right. You can see it says that no problem, but the missing thing is the light or electricity. Okay, so we can say light, but light without electricity doesn't work. Okay, so we have the electricity problem here, or lighting problem here. Okay, so the electricity works by the one of the applications of the thermodynamics. Okay, the applications that I have shown till now are all of them purely thermodynamics. Okay, this one is thermodynamic device, and all of its energy conversion. This one is 2, this one is 2. Okay, all of them are thermodynamics device. This one is also pure. Okay, so everything here is that application of the thermodynamics. Okay, here you have the cooling towers. Okay, and here you have the working stations, and somewhere you have here you have the turbines. Okay, so this is the power plant. Okay, power plant where you have the thermodynamics devices, right? And these are the pipeline systems for the power plant. And then comes the electricity generation. This is also a pipeline system, and here sometimes you can see the smoke. It is not smoke itself, but a condensed vapor. Okay, this condensed vapor. Okay, so this is the power plant, and this is the turbine. The turbine is the thing that you are producing electricity. When the steam or water comes, in fluid mechanics, it is water. I've said Pelton turbine or Francis turbine. In thermodynamics, the stuff that comes to these blades of the turbine is the steam. Okay, when the steam comes, this one rotates. Okay, as it rotates, and you will get, so this one rotates with some speed of omega, and from this speed you get the electricity from the generator. Okay, but these systems are very huge systems. You can see the size of it. So sometimes it can be the 60 meters, sometimes it can be 100 meters, large systems, and you get the electricity. And I can say that more than 80% of electricity of the world comes from this steam system. So steam. Okay, we also call this thermal power plant. Okay, so we also call it thermal power plant, but this is for the world. For Azerbaijan, it is more than 90%. Okay, Azerbaijan works this, more than 90% comes from this thermal power plant. But the rest, 8%, more than 8%, comes from water. Okay, so it is from Mingeshevir. This one is also in Mingeshevir. Okay, this one is also Mingeshevir. This one is also Mingeshevir. 98%. It is more than 98%, but the rest is from the renewable energy, solar energy, and a bit amount of wind power. And you can see the importance of this thermodynamic application, electricity. So we have the similar. It's not similar, the same, I can say the same one, but in a model. Very small size. You can see this one is I can show the components to you. This one is the boiler. Okay. And this one is the condenser. In the real power plants, they don't use condenser. They are using cooling towers. Okay. In YouTube, we can see videos of explanation of these systems. And also in thermodynamics too, we will see this system, how it works. And then you have also the turbine here. I have the turbine here. This turbine, okay. When it rotates, you get the electricity, power, okay. And then this power is connected to some source, and it goes to home, okay. And this is called the grid. And this system, this is the turbine. And here you have the steam. Steam comes from this pipeline. You can see the pipeline here. Steam comes from that pipeline into the turbine, and it rotates the turbine. As it rotates, you have the generator here. This generator gives you electricity, and you get the electricity to home by the power lines, power transmission lines. They are called grid because they are in the shape of the grid. Okay, so here you can't see the grid because it is at the back of this power plant. But in real power plants, also you have the grid electricity delivery system. Okay, good. So can you imagine life without electricity, which is the thermodynamics? I said more than 80%. This one is thermodynamics, and the 9%, 9 or 10% comes from the fluid mechanics. Pelton turbine, Francis turbine. In Azerbaijan, 90% thermodynamics and 8% fluid mechanics. This one is fluid mechanics, and this one is the thermodynamics. Similarly, this one is the thermodynamics, and this one is the fluid mechanics. And therefore, it is very important to know and to understand the concepts of the fluid mechanics and thermodynamics. In your real life, most of the devices, it uses electricity. The oven uses, motor uses, car uses, drill, okay, any working tools uses electricity, communication tools, your phone, TV, nobody uses radio, but anyway, floodlight, flashlight, different types of light, air conditioner, refrigerator, okay. Most of the systems uses electricity, and which is again as a result of the thermodynamics. And here we have another missing problem. Something is missing, and we are using horse for the solution of the problem. And that missing stuff is the engine. We don't know engine is if it's here or back. It should be here, okay, engine. The engine is not working properly. Therefore, you are using the horsepower. Horsepower. We are using the horsepower for the engine of the small car. But if the engine is working, thermodynamics is working, You have this good stuff. Okay, this is the engine. If you have seen engine before, these are the valves of the engine, where you have the delivery of the fuel, and these are the pistons. These are the pistons. You can see it presses against the mixture of air and the fuel. This one is also presses against mixture of the air and the fuel. And we have the connecting rods and the crankshafts, and these are the camshaft. You can see the lobes here. This one is the lobe of the camshaft. These are the camshaft and the camshaft. And this is the belt and the power, as a result of power of your engine that is driving the wheels of the car. And you have the crankshaft here. You can see the crankshaft here. It is in the form of the crank. Okay. And you have the gears, etc., etc. Again, this combustion, not the overall system, but the combustion part here, combustion, as well as the power part here, is thermodynamics. You see, it is very important process in thermodynamics, and you have to understand it. But in thermodynamics, instead of using this complex system where you have the valves, the cams, the lobes, etc., etc., we are using this simple system. Now, it is approximate of this one. You can see here you have the piston, the same piston as here, same piston as here. Instead of two pistons, we use one because the same process happens here. Okay, and then you have the crankshaft. You have here crankshaft, and you have the connecting rod. This one is the connecting rod, and you have the crankshaft, and then you have this one is the, you see that this part, this one is this volume. I can say that the displaced volume, but in simple terms, it is the volume of the car. For example, if you say that my car has a volume of 1.6 liters, it means that this part. If there are two cylinders, you have one cylinder here, another cylinder here, you sum them and you will get, for example, 0.8, 0.8, 1.6 liter is the engine volume of your car. Okay, you have the valves here. The valves are used for the exchange of gas and the fuel mixture. So here, gas and the fuel mixture comes, and this is the spark plug. You know the spark plug. Here we have the spark plug too. You know, it is valve. So we have the spark plug. That spark plug is, the name explains itself, spark. It is used for the spark and the combusting the mixture. When there is a spark due to high voltage, and that high voltage gives the fire, and you get the combustion. And if you have the combustion, and you have the moving car. Okay, so even in thermodynamics 2, we use this structure, but for thermodynamics 1, we use most of the time this structure. Okay? In this structure, you can see the piston is upside down. In that structure, piston moves up and down. This structure moves first down, then up. Okay, you can see the structure here, the similarity. And then this is the cylinder, and here you have the cylinder. This one is the cylinder with the displaced volume, and here you have the cylinders, and here you have the cylinders. And then you have the piston, I said, and the shaft here is there, and here you don't have any. We have the shaft here, which is the connecting rod, and then it is connected to the crankshaft. Okay, and then this is the cornerstone of thermodynamics 1. You can see 1 here because it gives the understanding of the thermodynamics, and it is also the historical, because the history of the thermodynamics started with engines. At the beginning of the 17th century, the people started to build the engines from the steam, and that is the time where thermodynamics has begun as a science. Therefore, in thermodynamics 1, we most of the time use engines as a historical stuff, and as well as it is easy to understand the problems in thermodynamics. And here also you have some missing stuff. So one guy is hitting the heavy truck, and the other one is the guys that are pushing the truck, and the one guy is busy with something else that nobody knows. Okay, anyway, so you have this good structure. So here you have also the missing stuff. That missing stuff is, of course, the science is not there. And the one more stuff is that is missing is the engine. Okay? But if the engine works, okay, so that is the application. That was the application of the thermodynamics. Okay. In this application, so here the engine of these cars are purely thermodynamic invention. Okay. So their timing and their cylinder volume, etc., speed and cooling system, all of them are thermodynamic invention. Good. And there is one more thermodynamic invention here. Let's see if it plays. Metabolism. Okay, metabolism is also thermodynamic stuff because at the end it is conversion of energy. If there is energy conversion, then it means that there is thermodynamics. You can say this animal runs, but it runs on water. You can see it runs on water. Run, run, run. There is some message. Okay, so it runs on water.
Run on water. The basilisk is called the Jesus Christ lizard because it can walk, well, it can run on water. It bicycles its hind legs, and the tail becomes a counterweight. It can walk.
Okay, so this is also the application of the thermodynamics. Here, the weight, the balance is not so important for thermodynamics. It is tail balances its forward part of the body. But here, the main important part is not the balance, but it is the metabolism. Okay, because metabolism is thermodynamics. Thermo 1. Why? Because here in metabolism, you have the energy conversion. Energy conversion. Because you eat food, that food is converted to your muscular movement, let's say in simple terms, motion. That is converted. This one has chemical energy, But at the end of this, conversion, you have this energy conversion from food to motion. Okay, that is thermodynamics 1. Okay, good. Another application of the thermodynamics. Okay. So these were the applications of the thermodynamics 1, and in thermodynamics 1 we will see most of the time the components of those systems, but in thermodynamics 2, that will be next year, we will not see the components, we will see the system itself. We will see the system itself and how the cycle works and how can we increase the efficiency. Here I have listed the systems that we have seen till now. We have the heating systems, we have the engines of the cars, aircrafts, ships, heavy trucks, etc. We have the cooling systems, refrigeration unit. For example, at every house, then we have the refrigeration unit, and the air conditioning, AC, we have it. These are all thermodynamics. Heating systems, we have the heat pump, car radiator, electricity generation, I have said it, turbine, power plants, etc. And the human metabolism, here I have said that human metabolism, but actually it is any metabolism, okay? Any metabolism that converts from one energy to another energy. Okay, so these are the thermodynamics. Okay, so even samovar, okay, this one is also thermodynamics. Okay? If you think about it, so you have here you are burning wood. Okay, this wood gives off its energy to water inside the samovar. Okay, therefore you have the thermodynamics application. And here you have again the water boiler, but this one is electric water boiler, actually heater, not boiler, heater. This is again application of the thermodynamics 1, and here you have the cold water, and here you have the hot water back. This one is the hot water. This one is again the thermodynamics because you are converting electric energy into the heating. But here the important stuff is that how much electricity do you need for heating. For example, here you have the 80 liters of water. Okay, and this electric water heater heats up to 80 degrees Celsius. Okay, and the question is how much electric power do I need to convert the 100 liters of water from 20 degrees to 80 degrees Celsius. Okay, this is very simple high school question, but at the end it is thermodynamics. And one more thing here is that you should select your materials very good, because here you have the heat loss. The system loses heat. Okay, it loses heat to the environment. So here you have good insulation. Here you need good insulation. Otherwise, this system heat loss will not use the same electric power that has been calculated. It will be more than that one. Therefore, here insulation is very important. In some of ours, you don't have good insulation. You can see that after some time, the water cools off. Therefore, you are burning the wood all of the time. And this one is the thermos that you know. It is also called, or it's also called the Dewars flask. Okay. This one is the generic name. The thermos is generic name. Generic name means that the device name is not the thermos, it is name of the company. Okay, this is the company. It is very similar to Colgate. Okay. When I say Colgate, it is not the meaning of the toothpaste, but it is the name of the company that produces. Similarly here, the thermos is the name of the company that produces this Dewars flask. Anyway, this is also the application of the thermodynamics, but here it is not purely thermodynamics, it is the mixture of the thermodynamics and the heat transfer. Why it is mixture? Because here you have the radiation problem too, because the heat loss is not by there is no medium here, no medium. Okay. And you are losing the heat of the system by electromagnetic radiation. This electromagnetic radiation keeps the system up to some time hot. Okay, for example, for 1 day, for 20 hours. Okay, that is a mixture of the thermodynamics and the heat transfer. You should find how many days, how many, for example, hours will be enough for the system to be cooled to 20 degrees Celsius. Okay? At the end, that determines the quality of your product. These are the applications of the thermodynamics. I have said the heating system at your home. If you have watched the heating system at your home, at one side you have this. Let me change the color of the pen. So you have the hot water into the system. You have the cold water out of the system. And this hot water, you can see here, it comes here and leaves. And then goes to another location here. And again down. Another location here, again. I can show all of them, but it is not so important. So it comes and it is collected here and leaves the system. Okay, let me connect it. It is again the thermodynamics, but it is again high school, but sometimes a little more complicated, because here you have, for example, 60 degrees Celsius or 80. Let's say that we don't know this temperature. The temperature is unknown. The approximate that temperature, the water lives at room temperature, 20 degrees Celsius. And the question is, what should be the temperature of the inlet water? Here you have the water. What should be the temperature of the inlet water to heat the room? That is a thermodynamic question. You should use the equations to find the inlet temperature required to heat the room, because this one heats the room. And you can see some more stuff here. You can see there is a plate here. You can see the plate. There is one more plate here. There is one more plate here. This plate, you know, it increases area. Okay. As it increases area, it is good for transferring heat. It is very similar to when you cool your tea in glass or plate. When you use glass for cooling your tea, it takes lots of time, but for plate, it takes less time because it has more area. Area is more, but it has less area. Area is small. In the similar manner, for heating systems of the house, we are using this this structure here. It is called fin. You are using these fins that helps us to keep the room hot. That is at the end the thermodynamic device, and the question should be what should be the temperature of the inlet water so that the room is at, for example, 28 degrees Celsius. And also number of these devices, that is heat transfer problem, but for simple cases we can deal with it in thermodynamics. Again, one of the good applications of the thermodynamics is the blood system, blood circulation system in your body. If you look at your, this is the structure of the blood circulation system in our body. And in our body, the incoming blood and the outgoing blood, they are very close to each other. Okay, so it means that when they are very close to each other, so what happens is that one blood, so this one comes from heart. Okay, let's say this one goes to, this one comes from heart, this one goes to heart, let's say. I don't know the exact location where it will go. At the end, it goes to heart. So the problem is the blood that comes from heart, it is hot, okay? And the blood that goes to heart, it is cold because it has circulated in our body and it has lost its heat. Therefore, it is cold. What happens is that this hot coming blood is very close to cold coming blood. So therefore, this one gives off its heat, some of its heat, to cold blood. Okay, and this cold blood increases its temperature, T increases, and helps our heart to work easily, because if it is cold, it is also dangerous for our body. Therefore, this hot blood that comes, you can see the similar picture here. This one is warm, and this one is cold, and this warm one heats the cold one. Okay, you can see. And therefore, you have the equilibrium, it's similar temperatures. It helps our body to keep it in good, it helps our body to be in good mood, as well as helps our heart. Okay. This again the thermodynamics question. The question should be that the length of this blood vessel, is important, because you have at the end delta T, and delta T should not be too high and it should not be too low. And it is a length problem. How long this blood vessel should be not to exceed the required amount of delta T. Delta T, I mean, here we have the 20 degrees, let's say 30 degrees, and here it is 32 degrees Celsius. Okay, this length should be in such amount that the temperature drop is not too high or the temperature drop is not too low. It should be in the optimal range. Again, it is a thermodynamic question. And here you have the back side of the refrigeration units. And modern refrigerators do not have this unit at outside of it, because they have enclosure around it, cover around it, and you don't see it. It is in all the refrigerators. If you are poor enough, you can see all the refrigerators at your home. But if you are rich, you will not see this one. Okay. Anyway, here again, it is thermodynamic question. Why? Because the cooling agent or the freon gas or refrigerant, it comes through this system and it goes in. Let me change the color of the pencil. It goes in that direction, and it goes in that direction, and it goes in that direction. You can see it travels zigzag. Okay, this one travels in zigzag direction. Why it travels in the zigzag direction? Because the residence time is important. Here also zigzag. You can see the zigzags. It goes here and it goes here. It goes. Zigzag is important in any heat device. Zigzag is important because it increases residence time. It's very similar to guest. If you have a good guest or if you have a good friend at your home and you want the residence time to be more and you want to spend more time with your friend. Similarly here, this one is hot. The fluid is hot. Okay, and this is good friend. If it is hot, if it is good friend, what I want is more time. I want to spend more time with the hot water. Therefore, I put barriers in front of the fluid. If there are lots of barriers, then it means that there are lots of time to reside together. If there are lots of time to reside together, it means that you will have good heat transfer. Similarly here, you see the zigzags. Therefore, you will have good heat transfer from the system to the environment, okay? Because it helps the refrigerator to work efficiently. And on one hand, this is important. And on the other hand, you can see there are also structures very similar to this one. You can see plates here. You have similar plates, you can see. And this is again called the fin. And the fin means the increase area. You are increasing area, and the more area means more heat transfer. Ladies and gentlemen. Ladies and gentlemen. So we have 15 minutes left. Good. So this is the cooling or the radiator of the car. This is again the thermodynamic device. So I will not talk about the components of the radiator. You can see in YouTube, or if you are interested, you can wait for our heat transfer lecture for the next semester. We will talk about radiator in more detail. But this is again application of the thermodynamics. Here we have the radiator, and this one is the fan. And by the way, the radiator is misnomer. Okay, misnomer means the name is wrong. Okay, name is wrong means why the name is wrong. Radiator means that the heat transfer here, there is heat transfer that happens inside the system. It is by radiation. This is false. The heat transfer here doesn't happen by radiation. It happens by another type of heat transfer, which is convection. We'll see in heat transfer lecture. Therefore, it is convector, not the radiator. This historical stuff. In the past, people believed that heat transfer happens due to radiation, electromagnetic waves, radiation. And therefore, they called it radiator, but it is not radiator, it's convector. Good. So this is another application of the thermodynamics. So you should select a good amount of you should, at the end, here you have the T high, and here you have the T low, and this the difference in temperature, and that is at the end the energy that you want to lose. This energy that you want to lose is a part of the system, and therefore you have to calculate this energy loss by the thermodynamics. Okay. And this part is also the part of your car, and it is heating inside heating the cabin of your car, and used in winter. Okay, we have finished with the applications of the thermodynamics. In some applications, the system, the overall system is. In some applications, the overall device is thermodynamics, purely thermodynamics, but in some systems, it's a mixture. Some thermodynamics or heat transfer is required, or thermodynamics or material science is important, or the thermodynamics or the fluid mechanics is important. So it is sometimes it's a mixture. We call it the thermal sciences, but in some systems, it is only the thermodynamics, pure. Okay, now comes the concepts in thermodynamics. We have a roadmap here, so you can see we have finished with the application areas. Now we are going to talk about the states, properties, and then specific volume, and then the zeroth law, and the temperature, pressure. So this will be till the end of the lecture. Now comes the first important stuff in thermodynamics, which is the control volume. What is control volume? Control volume is, in simple terms, is open system. Open system is called control volume. If it is closed system, it is called control mass. So from the names, I think we understand what happens. If you are controlling the mass, if the mass is fixed, then it is called the closed system. Mass doesn't change. If the mass changes, or it decreases or increases, it is called open system or control volume. Why control volume? Because you are controlling the volume. In most of the systems, volume is fixed, it doesn't change, therefore it is control volume. It is called control volume. But there are also possible that the volume is not fixed, it changes, it deforms, it expands, it decreases, etc. But it is control volume at the end, and our control volume is open system. In thermodynamics, the control volume, let me erase it. The selection of control volume is very important. Okay, the selection is important. You can select any kind, any control volume is enough, any control volume is right, but you should select a control volume such that the problem is very simple. This system is not open system, it is closed system. Therefore, we don't deal with control volume here, but we are dealing with closed systems here. I will add closed system here. So I can select in this system, my closed system, something like this one. It is possible. And we are showing the system with dashed lines. Okay, system with dashed lines. Okay. Why do we need control volume, or why do we need closed system? In statics or dynamics, you are dealing with particle, point. Say that this point has some weight W, and there is a force acting on it, which is normal force, and there is friction against its motion, which is F friction, and this one wants to move forward. It has some force in thrust in that direction, okay? But at the end, you are dealing with this point. At the end, it is point, particle, approximation, particle. In fluid mechanics, as well as thermodynamics or heat transfer, in all of these things, we are not dealing with points, but we are dealing with closed or controlled systems or controlled volumes. In other words, we have a system of fixed identity. Okay, we are dealing with that. So here, this structure cannot be written as point. It is false, okay, because this is a system and there is mass inside it. There is some rotating equipment inside it. Therefore, in thermodynamics or fluid mechanics, we are dealing with control volumes. And in, for example, dynamics or statics, selection of particles is important for force analysis. In thermodynamics, selection of the control volume or closed system is important for system analysis. Now I will show you 3 different control volumes and also closed systems, and you will understand why it is so important. But firstly, I should write, there are 3 types of transfer. You have the energy transfer. Energy can leave the system. You have the mass transfer. Mass can leave the system. Energy can leave the system as heat. Okay. It is also possible. Energy can leave the system as work. Or you can have the mass transfer. If no mass, no energy transfer, if it doesn't leave the system at the same time, let's say that, yes, this one is called the isolated system. Isolated system. If there is no mass transfer, if there is no energy transfer, it is isolated system. For example, in this system, I can select this one as like this one. This is my control volume. You can see this one is closed. There is no mass transfer. No mass leaves the system, no mass comes. So mass transfer is not there. If I look at the energy transfer, there is energy transfer inside the system. You can see this weight, if it is dropped, it falls down. It pulls this pulley with itself, and then this pulley rotates, and then this cable rotates. As it rotates, here you have the paddle wheel. This one is called paddle wheel. The paddle wheel rotates, and you will have heat transfer, the heat transfer into the system, because as it rotates, there is friction against it. It rotates in that direction. Friction is against in that direction. Therefore, no, sorry, in the opposite direction, friction against it, and temperature increases because it rotates inside water, and water resists it due to viscosity, and that viscous forces dissipate as heat, and it increases the temperature. As a result, you will have heat transfer, work transfer into the system. Work or energy transfer into the system. But there is no energy transfer from the system. Why there is no energy transfer? You can see these hatched lines. These hatched lines means that it is insulated. Okay, so you should be sure that there is insulation and there is isolation. Okay, Insulation means no heat transfer. No heat transfer. Okay. Insulation means no heat transfer. But isolation means no energy or no mass transfer. Okay, you should be careful about this one. And if it is insulated, it means that no heat transfer. If there is no heat transfer, it is called adiabatic system. Okay. In this structure, you can see there is no heat transfer because it is hatchet. If it is hatchet, there is no heat transfer from the system. System is insulated and adiabatic system. Okay. And this is selection for my control volume. This is one option, but I can select my control volume in a different case. Say that I've chosen this one. You know, these are arbitrary. You can select any control volume, but the wise selection of control volume is important. So if I select this one as my control volume 2, say that this one is control volume 1, this one is control volume 2, or closed system. Let's say system, not control volume, to be clear. It is possible I select control volume 2. I say that control volume 1 is not good for me, and say that control volume 2. I erase this one and say control volume 2. But in this case, you can see the difference. Now there is heat transfer. So heat transfer is there. It is not insulated because insulation is outside of this one. The system leaves, there is heat from the loss from the system, okay? And there is work transfer into the system. Again, there is no mass transfer. I hope you understand what I mean by the selection of the control volume. Now let's go back to another example. I can show you one more example. So the example is a thermos or the Dewey's flask. Now I select my control volume so that you can see. I select my system. Okay. From this system, if it is perfectly insulated, insulated means no heat transfer, no heat, and therefore adiabatic. Okay, but there is no perfect insulation. Whatever Dewey's flask or the thermos you have, it loses heat. Therefore, you will have energy transfer out of the system. Energy. If it is closed here, there is no mass transfer. If it is open here, then you will have mass loss. Okay, the mass leaves the system by evaporation. I hope you understand what I mean by selection of the system. Good. Let's select another system here, the samovar. So I select samovar system as this one. In this system, you have the Q, heat transfer, heat loss. And if it is not boiling, there is also the mass loss. But in thermodynamics, I have said approximations are very important. For example, in this system, mass loss is very small. And therefore, I can say that even if it is open, the mass loss is very small. Therefore, I can assume this one as closed system. Because this Dewey's flask is 1 liter, for example. The mass loss is 1 milliliter in, let's say, that 1 hour. In 1 hour, you only lose 1 milliliter of water. It is 0.001. It's very small mass loss. Therefore, I can assume that this one is closed system. Even for the samovar too, I can assume that this is closed system. And now comes the similar structure for the Ariston. You can select your system and you can analyze it. And even in this case, if it is perfectly insulated, Ariston will not lose heat. I can select control volume, something like this one. And if it loses energy, and if these pipelines are closed, and then it means that it is closed system. Okay. These are simple introductory selection of the control volumes. And there will be some control volumes that you will not be able to select the correct one. Okay, let's select one more control volume. For example, this one. You can see it is very easy. Again, I select this one. Okay. In this control volume, you can see there is mass transfer into the system, there is mass out of the system, and there is energy transfer from the system, energy, and therefore it is open system. There is mass transfer, there is heat transfer, and there is this open system. Good. Now I think that you have understood the system. For this system, I can do one more funny thing that you have not thought about it. For example, I can select my control volume or system, something like this one. I can select my control volume, something like this one. It is also possible. Nobody can say that you cannot select this control volume. You can even select the control volume of the universe. Okay, say that this is Earth, this is Moon, and this is universe overall. And there is somebody. Let us say that you are here, and you are doing this experiment. Okay, you are here with your experimental tool. You can select this control volume, universe. Okay, you can select any control volume. It is okay. You can select any control volume. If you select the universe, everything inside that universe, and including you, then this universe is there is no energy transfer. No energy transfer, because universe is including everything. You, your experimental stuff, the moon, sun, the earth, everything. Okay, therefore no energy transfer as well as no mass transfer. Okay, therefore universe becomes in isolated system, isolated. There is no any type of the transfer. Okay, now let's go back to our system. And this is our system. We have included the overall stuff here. And from the boundary of our system, we don't have any transfer of energy. Okay, we don't have any transfer of energy, and therefore this system becomes the insular. So this system, no energy transfer. Okay, this one is the first thing, and then second thing is that there is no mass transfer, and the system becomes isolated system. But if it moves, then the gravity will act on it, and the gravity will pass the boundary of your system. Then you will have the work transfer or energy transfer from your system. And next comes the continuum properties, states, the path, and the process, and the cycle. These are the another important stuff of the thermodynamics. And I have, so let's see the time. Yes, time is, so we have started late, and therefore we should finish 8 minutes earlier. And if you have any questions, you can ask. If you don't have any questions, I will leave this one for tomorrow, and tomorrow we'll talk about these concepts in more detail. If you have questions, you can ask.
Diyebilirler ki bütün enerji kabul edilmeler ve temperatur